All right, so in this lecture, we're going to introduce some more concepts related to the mean squared error as we introduced in the previous lecture. So in particular, we talked about MSE in the previous lecture and said that might be a quantity we'd like to minimize. Well, if we're trying to minimize that quantity, what I really might mean is what value of the MSE is good enough. And that's going to lead us to this statistic, which we'll introduce, called the R-squared statistic. Okay, so that's the basic question we're trying to answer here. How low does the mean squared error have to be before we consider our model accurate, or before we say it's low enough? Well, that's a very hard question to answer. And in particular, it depends. There's no one right answer. The MSE is going to be proportional to the variance of the data. So what does that really mean? Imagine you were trying to predict something like a star rating. And if you are typically off by half a star or something, you might consider that to be an accurate prediction. Your MSE might be something like a half or a half squared. Now, if you're trying to predict ratings out of 100 and the values were off by 5 points, again, you might consider that to be a good prediction, but your mean squared errors would be much larger. You're dealing with larger values of the labels, so you'll have correspondingly larger values of the error. That's exactly what I mean when I say the mean squared error is proportional to the variance of the data or the variance of the labels. Okay, so can we write down a few equations to demonstrate that point? We need a few things here, just the mean, the variance, and the mean squared error as we defined on the previous lecture. So just to remind ourselves of what those are, the mean, or y bar, is just going to be the summation over all of my data points from 1 to n of my label. So this, when I say the mean, I'm talking about the average value of the label. And I'll just divide that by n. Okay, so the variance, precisely speaking, is a measure of the average data points variation from the mean. So that's going to look like the following. The variance of the label is going to be equal to, again, an average over all of my data points of the difference between the mean value and that data point squared. That's our definition for variance. And mean squared error, just to remind ourselves from the last lecture, is going to look like the following. It's going to be the sum of all of our data points from 1 to n of the model's prediction xi dot theta minus the label squared. And we're averaging that by dividing by n. So already you might start to see this relationship between the mean squared error and the variance. The second and third equations here look very similar to each other. The only difference is that in the second equation, I have this expression y bar, or the average value, and in the third equation, I have the prediction of the model, xi dot theta. So that's the relationship between the mean squared error and the variance of my labels. Okay, so here's the same thing, just written down a little bit more neatly. All right, so what I basically showed is that the mean squared error is going to be proportional to the variance of the data. So a more robust error metric, which is not going to be proportional to the variance of the data, would just be to normalize our mean squared error by taking the MSE and dividing it by the variance of our labels. So this is going to be an expression which is known as the fraction of variance unexplained. The point of this is it's going to give us a measurement between 0 and 1 that measures the difference between a trivial predictor, or one that just predicts the mean all the time, and a perfect predictor, or one that has no error, or an MSE of 0. So to think about a trivial predictor, if I just predicted the mean everywhere, then my mean squared error is going to be equal to my variance. So the denominator will be equal to the numerator, and the fraction of variance unexplained will be equal to 1. Otherwise, if the mean squared error was 0, then the numerator would be 0, and the fraction of variance unexplained would be 0. Okay, so this is a little bit more reliable. It's just an error measure that's going to give us a value between 0 and 1 to interpolate between a trivial and a perfect predictor. Another commonly used error measure is what's called the R-squared statistic. That's very closely related to the fraction of variance unexplained. Really, it's just 1 minus the fraction of variance unexplained. So this is just doing the opposite thing, where it's going between 0 for a trivial predictor and 1 for a perfect predictor. The reason we have these two different definitions is just due to different ways that one can arrive at these different statistics. Okay, but in this case, we say we have an R-squared value of 0 if we were to just predict the mean everywhere, and an R-squared value of 1 if we were to make perfect predictions. So a quick follow-up question, would it be possible to have a negative value of this R-squared statistic? So could we do worse than what we said is a trivial predictor? All right, so our definition of a trivial predictor was one that just predicted the mean all the time. If you'd like to estimate sentiment or a star rating, the most trivial way you might do that is just to compute the average star rating and predict that everywhere. But could you actually do something worse than that? All right, so a trivial predictor has an R-squared statistic of 0, but we could have something worse than that. For example, if we use the mean, we get an R-squared statistic of 0, but if we use anything other than the mean, we would actually get a negative R-squared statistic. So if we predicted all ratings 0 or all ratings 1 or all ratings any other value besides the mean, this would kind of be worse than our most naive or our most trivial predictor, and that would actually have an R-squared statistic that was a negative value. But for any reasonable value of a predictor you should invent, you should typically get an R-squared between 0 and 1. Okay, so that's the end of this lecture. Really all we did in this lecture was to introduce these two new statistics, the fraction of variance unexplained and the R-squared statistic, which is basically equivalent. And we explained the relationship between the mean squared error, the mean and the variance. So how can we develop some kind of statistic that is normalized to the variance of the data and will take this sort of calibrated value between 0 and 1 corresponding to a perfect or trivial predictor?